Okay, our next three sessions are going to be closely related. So we got complex numbers, then we have polar coordinates, then we got vectors. Okay, so let's first kind of put this in context. A complex number, you might remember, has an imaginary piece. Okay, so for example, a real number. Real numbers are what we've been working for in this entire class, right? Numbers like the square root of 5 and 17 and 1/4. And that set is actually enclosed in the complex number set. Complex numbers, it's really a subset of the complex numbers, where a complex number would have subsets of what's called imaginary numbers, like 3i. Okay, and then so let's talk about I real quick. Remember, if I had a solution to this equation, x squared equals 4, we might say, well, I can take square root of both sides, and I get an answer of plus or minus 2. Those are all real numbers. But you say, well, wait a minute, what happens if I had x squared equals -1? I'm stuck, right? I can't solve that in the real number system, but if I define a new number, square root of -1, we say, well, I can't square a number, right? I can square 2 and get 4, and I can square -2 and get 4 in the reals. But in the imaginaries, or in the reals, I can't square a negative, or I can't take the square root of a negative, rather. But in the imaginaries, I can do that. So if I say, well, wait a minute, what if I give this guy a name? We'll call it I, right? So plus or minus I, if I square root both sides, the square root of -1 is I. And this allows me to keep working with these problems. And there's actually a lot of applications that go with this. It's a way to think about algebra in like 2 dimensions, right? This is all one dimensional. This would just be, these solutions are on the number line. 1, 2, 3, -1, -2, -3, and so on. These guys are going to add a dimension to this when I combine these two sets in a complex number. That leads me to complex number. It would be like a partial real number combined with an imaginary number. Okay, so so the pure imaginary is a subset of complex, the pure real are a subset of complex, and a complex number would have both pieces to it, a real part and an imaginary part. Okay, and this will allow us to do a lot more with our algebra when we think of it in 2 dimensions. Okay, but for us, we just got to become familiar. We need to know these properties. This is our first thing that we need to know. Right there, square root of -1's I. We'll see that come up a lot. And then, of course, if I square that, this is a unique property to the real imaginary numbers, that us squaring a number gives me a negative result in the reals, right? And that's an interesting part too. I square an imaginary number and I'm back in the real number system. Okay, so that's what a complex number is. They look like that, right? It's like we'll generalize this here shortly. It'll be a plus bi, where this is the real component and this is the imaginary component. And we could just have a regular real solution or a pure imaginary solution, and they would also be considered complex because they're subsets of complex. Okay, and we're going to look at that. I have this graph up here. We're going to look at that in graphically, and it'll help us with this 2-dimensional concept. And why are you studying these? Well, we're not going to do any of this. Sorry, it's a little off center here. This is what it's good for. Let's see. Sorry, I just can't get this in the window here. Move this over. There it is. Okay, and you have access to this file, so you can read these. I won't spend a lot of time on this since we're not actually going to be doing any of this stuff. This is what you get into once you hit kind of more advanced calculus, or if you do any other math complex analysis, when you kind of do calculus in the complex numbers. Okay, but this is just an idea. They're actually quite useful. Unfortunately, we won't really see how useful they are at our level pre-calculus. Okay, we just need to be able to do some algebra with the complex numbers. Okay, so first I want to just think of these as how we would graph them. So here I am applying the two-dimensional grid to complex numbers. So first be real careful. This is not the XY plane. This is the complex plane. Okay, so we call this the real axis and the imaginary axis. Okay, and what I started this discussion with is the next three topics are closely connected by this way of graphically thinking about them. That is complex numbers, which we're studying now. And then next we're going to talk about polar coordinates. And we're going to be able to talk about polar coordinates in the same way. That is, we're going to be able to graph them in two dimensions and look at them both in their Cartesian form or XY form and their trig form. Okay, we're going to get there. And then we're going to talk about vectors. And same thing with vectors. We'll define a vector in both Cartesian XY form and trig form using an angle. Okay, so let's talk about that. So 6 plus I, if these are all the imaginary numbers, right? This is 1i, 2i, 3i. This is negative 3i. And this is the real numbers, and you cross them, each one dimension, you get two dimensions. Then 6 plus I is right here. 6 plus 1i. That's point A. Negative 1 minus I is right here. Okay, we're going to do operations on these. 5i would be right here. That's C. And negative 10 would just be a pure real number. That's right here. Okay, so we're going to do operations. That's our goal. We want to do, really, in this class, we're just going to do, we'll kind of skip addition and subtraction. That's easy. And we're going to look at ways to multiply, multiply, divide, and then raise to power, and then take roots. Okay, that's our goal here. I want to multiply two of these numbers together. I want to divide two complex numbers. I want to raise a complex number to the 5th power. And we're going to look at how to do that in what's called trig form. Okay, so this is not trig form. This is Cartesian form or XY form in our regular two-dimensional plane. So let's talk about this trig form. Okay, so let me start with B. Negative 1 plus I. That's right here. Okay, now this is a point in space, two-dimensional space, right? I say negative 1, go back 1, and go up 1. And I know exactly where that guy lives. Now, what if I wanted to point to that point in two-dimensional space, but by a different way? Think of this. This is actually a really interesting question in math. And like I said, this follows from polar form. It might make sense to do the polar form. In my mind, polar form would probably be better to do first, but I'm just going with the textbook. It covers complex numbers first. Okay, so just in general, I want to point to a place in two-dimensional space. So I'm pointing to this spot. So I could say, okay, how do I get here? You go back 1 and go up 1. There I am. What if I wanted to use an angle? I could say, well, there's two other directions I could give you. It's a really interesting result if you think about this, okay, what I'm about to tell you. I say, okay, well, let's go this distance from the origin and this many radians. And I'm pointing to the same space, or the same point in two-dimensional space. By the way, when you get to Calc 3, you're going to do this all over again in 3 dimensions. Okay, it's very similar. Okay, so you tell me what that angle is. You should know that. That is, well, if you know this is 1, distance 1, and this is distance 1. negative 1, 1. Our old form of trig, or now our new form, this is 1i. Doesn't really matter. It's just as long as you can find the angle, but the distance here to here is the same. Okay, so what I need to do first is find this distance, which is simply the hypotenuse of the triangle, or the modulus of the complex number, it's called. Okay, so does this make sense? I'm going to call this complex number z, common letter used for these. Z equals negative 1 plus I. And then the modulus of d, we can't use absolute value bars. It's the distance from here to here, okay, which I said use Pythagorean theorem. You could do negative, you know it's going to be positive. But you probably already knew this. This is the same trig we've been doing a lot. That has the distance root 2. Okay, and now you should be able to find the angle. Now I can give you a formula for the angle, but I'd rather you just be able to figure it out. And take a quick graph and figure it out. You say, well, wait a minute. That is in quadrant 2. And this is a reference angle of pi over 4 because you recognize this triangle, 1 and 1, which means the angle is 3 pi over 4. We're going to call that theta. Okay, I hope that makes sense how I got that. That's just using trig that we've done before. All right, so now this complex number in Cartesian form or XY form, so the X value is the kind of the Y value, think about it like that, can be written like this. Let me show you the trig form. It's the modulus, and then cosine of the angle. This is going to look real messy. I times the sine of the angle. So first of all, you can say, wait a minute, how does that help? That looks really messy. I'm going to show you how useful it is here in a minute when we start doing these operations. But first, let me just convince you that these are the same thing. How could this be the same as this? They're the same. I'm using that equal sign. We don't use that lately in mathematics. Okay, so let me just prove it to you. I'm going to do some quick trig here. Good practice for us. These are really important to know. Cosine of 3 pi over 4, that should be root 2 over 2. And it should be negative since it's in quadrant 2. And then I have I. And the sine of 3 pi over 4 is also root 2 over 2, but it should be positive. Now let's say I ran this through. Root 2 times root 2 is 2. 2 over 2 is 1 times that negative. Same thing here. Root 2 over 2 times 2 is root 4 over 2, or 2 over 2, which is 1. And there, with a little bit of trig, I've showed you they're the same thing. So this and this are the same. And this is the lesson here. This is the trig form of this complex number. They're the same number. This is the trig form of that.